Hello and welcome to this design practice 2 module 23. I was talking about sensor and actuator design, and we had designed various micro valves and micro pumps. We were left with some of the other displacement kind of pumps and how we designed them, particularly at the microscopic length scale. And today I am going to talk a little more about peristalsis and then probably some other non-mechanical principle, for example thermocapillary or electrowetting effects. So, where we do the same effects, or we take the same effects as we did in the valving case and start doing some pump designs based on it. So, let us first look into the very basic scheme that is deployed across a lot of applications for creating microflow transport or microfluidic transport, and this is a displacement kind of a system which is otherwise known as peristaltic micropumps. Now, I would like to just illustrate here that peristalsis happens even within human beings, and physiologically the intestines are supposed to perform the bile movement within our body through the scheme of peristalsis. So, it is about a traveling contractile. So, let us say if we had a flexible pipe and we are creating pressure on a certain area of that pipe, so that the pipe contracts, okay, and then move that contracted area forward or in a forward direction in a continuous manner, then obviously the pipe being filled with fluid on both sides of this contractile would actually have fluid getting displaced in the direction of travel of the contractile, whereas as the contractile moves forward, the space that it creates at the back would have again a pressure difference, because of which there would be flow into the region which is just at the rear end of the contractile. So, at the rear direction of the movement of the contractile. So, this is a continuous peristaltic system, and you can actually produce an effect in a slightly different manner by using a flow geometry through which you could discretize this contractile effect, and this is shown in this particular illustration here. Let us say there is an inflow which is happening in a channel, which is this is the channel which is colored in blue, and it is being overseeded by a set of chambers which can expand and contract, maybe through pneumatic actuation. In this particular case, we could have again a controlled valve which bleeds in air into such chambers, thus inflating. So, the idea is to create a discrete contractile. So, as one of these chambers inflate, you see the inflated condition being given here. It will actually pinch, because this channel down here is flexible. So, it will pinch on the channel to create a contractile effect, and then you can have one part of the channel contracted while the other is being contracted. So, that now the fluid does not move in this direction anymore, and it starts moving only in the forward direction. And in this manner, if I could do 2 at a time, and then at a certain frequency, I should be able to transport fluid from the inlet side to the outlet side. So, this is exactly how you can operate a discretized fluidic system, and obviously it demands a lot of actuation, because all these are air actuated or pneumatically actuated, where cylinders are being inflated, deflated, typically in a material which is flexible, and creating a pinched effect on another set of flexible channels over which these cylinders are mounted. So, we want to somehow model this, design this to estimate that because of such a contractile and a travelling contractile, what is going to be the outflow for every such contraction to happen within a flexible microchannel. And for this purpose, I have a problem which has to be designed for. There is a peristaltic pump having 3 pump chambers, and there is a circular unimorph which is let us say piezo discs and actuators. In this particular case, they bend and deflect into the chamber over which they are mounting, and so such a bending would create a volume outflow of the confinement of the chamber over which this uniform is being stationed. just as is being represented here. For example, this is that disk and this is placed over a chamber. Okay, this is the chamber over which this disk is placed, and because of the mechanical action as the piezo disk is actuated through a voltage signal, there is bending. Okay. So, the piezo disk bends in this manner, and over the outlets on both sides of this chamber, it initiates the fluid volume which is present probably inside the chamber to exit the chamber. So, we want to determine that because of the bending of the uniform disk mounted over such a chamber, given some parameters, for example, the membrane dia of 4 millimeters, for example, and the membrane frequency of 100 hertz, we want to determine what would be the flow rate that it creates every time it bends and discharges. We can assume that there is no back pressure, and the gauge pressure between what is inside the chamber and outside is 0. Both of them are done at atmospheric pressure conditions. We further assume that there is a maximum membrane deflection of about 40 microns, which the univalve can bend up to, and which would create this kind of a volume flow condition. So, we assume the membrane. So, let me just start the computing here. So, we assume that the membrane deflection follows, it is of course a circular membrane. So, this is from first principles, particularly solid mechanics. So, it follows the deflection function d at certain radius, where d is this displacement. So, we were talking about a uniform displacement of the circular disk d. Okay. So, the d can be at various places from the center here to the sides, and these are different d's. Okay. So, this d function as a function of the radius here is related to the maximum deflection which is there in the center. Okay. So, let us assume this deflection right here to be d max times of 1 minus small r by capital R square, capital R being the final radius of the unimorph and small r being the point at which the deflection d is being measured. Okay. So, square of this. So, when we talk about estimating the volume that is pushed out because of such a deflection, so the volume delta V can easily be given by a double integral both in r and phi. We assume that the distance r, let us say this is how the disk is stationed or positioned in a xy plane, and there is a certain distance r which has happened at a particular angle phi. So, we can actually try to compute what is going to be the volume of deflection at this particular radius, and we assume a very small element at this radius from r to r plus dr. Okay. So, let me just write it again in a little better manner. So, let us say we are trying to talk about r and r plus dr, okay, as two elements. This is the whole disk which varies between 0 and r probably. So, this right here is r plus dr, and we want to find out that if supposing there has been a movement of this radius vector by an angle delta phi. This was phi, and so this movement right here, which is describing an element, okay, which has been created by virtue of such a displacement. So, let us suppose we are looking across this particular disk positioned in the xy plane with the disk centered about the origin, and we are talking about a radius vector small r at which the deflection is to be measured. We want to find out the deflection causes what kind of volume change by virtue of the disk getting deflected, okay, and the deflection happens out of plane into the z direction, for example, in this particular case. So, we take two neighborhood points to formulate a small element. Let us say this point right here happens to be r plus dr, and the radius vector, which was actually at phi, goes by an additional d phi angle, because of which a small element is traced out like this, and we want to find out this shaded element and what kind of volume displacement it has caused. And so, the best idea would be the delta V in this particular element can be represented as the deflection at the particular point. Let us say we assume this to be, because of the deflection and because of the miniaturized nature of the dr and the d phi, we assume this element to have a total breadth of dr, okay, a total length which is given by r d phi, okay, r d phi is the length, because obviously d phi is the distance which has been moved and by a radius r, and then of course we have the distance which it has, or the total amount of distance or the height that this element has moved is dr. So, I am estimating that this particular element is a cuboidal element just because of the minuscule nature of the element, and then we try to integrate it in the whole over phi as well as over dr. So, you can see there are two variables. So, the phi varies between 0 and 2 pi, and obviously the dr would vary between 0 and r. So, if we solve this double integral by substituting d max 1 minus small r by capital R square whole square r d phi dr, we are left with an expression 2 pi. So, this is the closed loop solution, 2 pi by 3 d max square of r, and if I calculate, this is the total volume because of the deflection which would happen to this particular piezo disc on giving a voltage signal. This happens to be 3.33 10 to the power of minus 10 meter cube. Now, such a deflection is being carried out at a relatively low frequency. So, at the relatively low frequency of 100 hertz, we can safely assume a linear relation between flow rate and pump frequency. So, we can assume Q is delta V times of F. Typically, the frequency, as the frequency increases, there are going to be inertial delays, and so it may not be necessarily linear at that point. So, we just assume here, because 100 hertz is a very small frequency, we can assume the inertial delays to be neglected or very small. So, we have 3.33 10 to the power of minus 10 into 100, that is about 2 milliliters per minute of discharge rate. Or if we wanted to see what is a meter cube per second, it will be 3.35 10 to the power of minus 8 meter cube per second. So, that is how you compute how a peristaltic pump, through a certain actuation which is made again in electrical manner, would be able to give a certain delivery, a flow delivery against atmospheric pressure. So, that is how actuator design for peristaltic micro pumps can happen. I would also like to give another non-conventional or non-mechanical micropump concept, which is based on the Marangoni effect, is the thermocapillary effect. Let us say we want to create a thermal bubble inside a capillary. You already know how this effect was earlier illustrated for showing how to block the flows or valve the flows. So, the capillary channel in this case has a radius of 50 microns, and the temperature. So, let us say there is this channel here, right here, it has a 100 micron diameter, 50 micron radius, and you have created a bubble here through either a thermal phase change or electrolytic phase change, and the temperature at both ends of the bubble are 100 degrees Celsius and 50 degrees Celsius. So, let us say there is T2 and T1, this is 100 and this is 50. So, as per the thermocapillary effect, there is going to be a flow of this bubble towards the 100 degree case because of lesser surface tension on the higher temperature side. And if supposing if we were to use this bubble as a driving bubble for moving the flow across which the bubble has been spread. Okay. So, it may as well carry as a plug the flow behind it, thus creating low pressure everywhere it goes and letting the flow follow it, and also on the other side pushing the flow out. So, it becomes an inlet outlet micro pump. So, in this particular case, for designing the actuation, we want to determine the driving force of the bubble, surface tension values are provided. So, sigma at the air water interface is 58.9 when okay. So, let me write it as a function of the temperature. So, sigma at 100 degrees Celsius is 58.9 Newton per meter, and sigma at the 50 degree Celsius mark is 67.91 Newton per meter. So, these are the two different sigmas which create such a driving force, and I would like to look at what is going to be the pressure difference at the two ends of the bubble. So, the pressure difference you must remember for the bubble to survive is represented as 2 sigma by r. So, at 100 degree end, this delta P becomes equal to twice times of sigma 100 degree Celsius by r, and at 50 degree Celsius side, this delta P becomes equal to again twice sigma 50 degree Celsius by r. So, these are calculated as 58.9 divided by the radius is a 50 micron radius capillary. So, the bubble size should also be 50 microns for the pumping to happen as the bubble moves forward. So, it is 50 10 to the power of minus 6. And similarly, here this is 2 into 67.91 by 50 10 to the power of minus 6. So, these are the two different pressures which are there at both sides. Obviously, this is a higher pressure, and so it will push the bubble forward towards the low temperature. So, the total actuation force which will be there is again what is going to be the, let us say these are P1 and P2. So, delta P2 minus delta P1 times the total interfacial area of the bubble A, and if in this particular case we assume the pressure to be perpendicular to the surface of the bubble. Let us say the pressure is coming and the contact angle is basically 0. So, you can assume these to be somewhat flat at both the ends, okay. And so we can approximately take this to be the cross sectional area, and this is pi r square, of course. So, pi times of radius being 25 microns, 25 10 to the power of minus 6 square. So, when we compute this number here, we get 0.9 micronewton. So, this is about the force which will be needed to move a bubble through heating the bubble differentially on both ends, which is again a non-mechanical version of the actuation strategy that could be utilized for the purpose of this particular pump. So, I am going to close on here and probably start the next lecture with a few more descriptions of different schematics of micro pumps, as well as some fundamentals of gas sensors. Till until then, thank you very much.